Hey everybody, how's it going? Let's see if we're up and online. We are up and online. Okay, so um, welcome to online office hours. The thing about the thing this week is that it's how should I put it? Midterm's over. You learnt a lot. You had to do a lot. You're all done being focused on physics, etc. The other class is a little bit ahead of us because of how the long weekends worked out. So the stuff on the assignment that's due on the Mastering Physics assignment, it's the calculations are very straightforward. The founding concept is the one we talked about today, essentially, which was how work is done. Force pushing on an object, and then if the object moves in that direction, that force will give the system energy. And if the thing doesn't move in the direction of the force, then no energy is given. Okay? So these questions come up in a variety of ways during the assignment. I don't want to kick this assignment down to be due next week, even though we're kind of covering it this week in the course. I might, depending on how Friday's lecture goes. But I think this assignment has 5 questions on it. And you already know how to do 2 of them, I think. There's some power stuff. So I thought that we'd go through questions like it today to get you up to speed on how to do them, because they're not very difficult. So like I said, I could, and if it comes down to it, I might kick this assignment down to be due next Friday, and next week goes, I don't know, we'll do something. I might shuffle the assignments around. But as far as things go, I think that you should be able to do the whole thing by Friday after class. These calculations are fairly straightforward, and we've got to move on to other things ASAP. So the questions are written down at the bottom. If you have any questions, you can, as always, ask online, ask the live chat. So, question 158. Page 158, question 20, I guess we're going to start with. So, without further ado, let's start. 20 goes like this. How much work does gravity do on a 2 milligram raindrop as the drop falls to the ground from a cloud 2,000 meters above the ground? Okay, so we need to know what delta y is, and we need to know what the force of gravity is. They're both pointing down, so it's going to be positive work. mg, so it's 9.81 times 2, okay, so this is milligrams, so that's 2e minus 3, and we're used to using kilograms, so this is 2e minus 6 kilograms. So the force on this is 9.81 times 2e minus 6, 1.96 e minus 5 newtons. Delta y is equal to 2,000 meters, which isn't very far for a cloud. And so the work done is the multiplied together, Fg times delta y. So it's 1.56 e minus 5 times 2,000. So 0.0392 joules. Okay. So, oh, the stream health is kind of going gronky. Let's see if we can, hold on. Yes. Okay. Well, I don't know why the stream's all weird. Because we are attached to the internet and we're doing good. Oh yeah, the internet's pretty slow. I don't know why. I'm on a wired connection. Yesterday I was having super troubles with the online office hours. And I phoned services and they said, oh here, hold on a second. All right, I'm back. Long story short, I'm plugged into the internet now like a troglodyte, but it seems like it's a little bit better. Let's move on to the next question. Question 23. A 55-kilogram acrobat must jump high and land on his brother's shoulders. To accomplish this, he leaps from a crouched position to a height where his center of mass is 1.2 meters above the ground. His center of mass was 400 millimeters above the ground in the crouch and 900 millimeters above the ground when his feet leave the ground. What's the average force exerted by him on the ground during his jump, and what is his maximum speed? Hey, that's a fun question. Okay, so let's start by drawing a diagram. Okay, so here's the idea. You got the acrobat, and he's crouched, and then he's not crouched, jumping. That's his foot. And then he's jumping in midair. What they're giving us information about is the center of mass, which is here, here, here. And so what they're saying is that this one is 0.4 meters above the ground. This one is 0.9 meters above the ground. And this one is 1.2 meters above the ground. Okay, so how do we do this? This is a great question, super fun. Here's the thing. The system, what should we consider the system? Well, there's two ways we can choose the system. One of them is to choose the acrobat, and then the Earth as a system in itself. We just do the Earth. But you know what? Let's okay, hold on. let's identify three things that are doing stuff. There's the center of mass of the acrobat, there's the earth, and then there's the legs. Converting chemical energy into forces and stuff. So the deal here is that when we're sorting out work and energy, we start by defining a system. And defining a system actually divides the system not only into whether potential energy exists, but also whether a certain force is an external force or not, right? So if the center of mass and the earth are a system together, then we know the system will have gravitational potential energy, right? If the system, and in this case the legs will be pushing stuff. External force. I don't really like that. You know what? Let's just identify him alone as the thing, and then we'll go gangbusters that. Okay, so the system is just the acrobat, including his legs. Okay. So there's two domains in this thing. At the start, there's two forces on him. There's a force from the legs, and then there's a force from gravity. Once he leaves the ground, there's only the force from gravity. Both of these so I guess we're not including his legs as part of him. We're assuming his legs are massless. Both of these things are changing the energy of the center of mass of the acrobat. So what are they? F gravity points down, and it has magnitude 55 times. And put in 1. 540 newtons downwards. His legs push upwards. I don't know how strong they are. I don't know how strong that force is. Okay. So the idea here is that there's two parts of the work here, in essence. During this part of the trial, when he's jumping, there's work done by the legs, and there's work done extracting energy from the system done by gravity. And in this part, there is only work done by gravity. Okay? So here's the fun thing. We can easily calculate how much energy was extracted from the system, center of mass. We can easily calculate how much energy was extracted from the system from gravity. Okay? So the overall change in height here from this part to this part is 0.8. 0.8 meters. It's in the opposite direction of gravity, so the work done by gravity is minus 0.8 times 540. 432 joules. So we know that over the course of going from here to here, gravity is going to eat this many joules of energy. Where did the joule energy come from? Well, at the very start, during this part, the jumper doesn't really have any kinetic energy, right? And it's just center mass, so there's no configuration energy either. And so at the very start, at this point in time, whoops, he's got no energy at all. So where did this energy come from? all of this energy came from the legs doing work. So W legs gave them all that energy to spend on going up in the air. So that's going to be the force is upwards, and the distance traveled upwards is there. Delta y is equal to plus 0.5, right? And I don't know how big the force is, so, but I do know that they're aligned with the displacement 5, so it's plus times F. So the force is 433 divided by 0.5, 866 newtons. So that's how hard he needs to jump to get this high in the air. Right. So that's the average force exerted by him on the ground during the jump. What's his maximum speed? Oh gosh. So in this part, his energy is always decreasing, so his speed's going to be decreasing. So his maximum speed is probably going to be that part. So when his feet leave the ground, the energy is going to be the initial kinetic energy, 0, plus the total work done. And I can calculate each of these. For instance, I know that his legs have given 433 joules. And I know that gravity extracts 540 times, how much work has gravity done from here to here? 0.5. So his energy at that moment is 433 minus 540 times 0.5, 163 joules. That's how much energy he's got at this moment. And that's the most kinetic energy he's going to have. So this is 1/2 times his mass, v squared, so v is equal to 2.4 meters per second. That's his maximum speed. All right. Any questions? One person watching? No questions. Yeah, so this is fun. There's other ways you can do this. If you wanted, you could have used the systems, the Acrobat, and the Earth together. And then there would be gravitational potential energy and kinetic energy. But this system wouldn't be closed because the legs, I guess, can do some work. The ground doesn't move as the legs push down, but the body moves as the legs push up. Let me just state this. All right, so here's your COM. Here's your legs. Here's the ground, okay? According to Newton's laws, the leg is pushing up with the same force as pushing down on the ground. In terms of work, though, this position doesn't move at all, and so it's doing no work. This part of it does work because as the legs straighten, the center of mass moves. And so you can think of the legs as a separate part of it. I guess you assume that it has no mass. But then the idea is that the change in the total energy is just done as the work done by the legs. It's fun to do that. It's fun. It's especially, it might be actually easier to do that because you know exactly how much energy that has because you know the maximum height. And so you can figure out how much gravitational potential energy it has. And so, you know, it went from having no gravitation, no energy, no kinetic energy initially, and some known gravitational potential energy. And so you can calculate the amount of work that gets done, so the amount of energy added for the system to go from not moving at this height to not moving at this height, and then so on. All right? You want me to do that? Sure, let's do it. So I'm going to redo this question using this system. And my emphasis here is just that, like, the way you choose your system will define which forces are forces from the environment on the system. And those are the only forces that can add or subtract energy from the system. So if this is the system, it's not closed because there's legs there and the legs can do work. But E at the end is the kinetic energy plus the gravitational potential energy. So this is after it's jumped. When you go from the jumping part to the non-jumping part, and you're just kind of free falling up, the total energy is conserved during this part of the motion. So at the top of the arc, 0 kinetic energy. Gravitational potential energy is 55 times 9.81 times 1.2, 647 joules. So at the end there's, here, hold on, let me draw a diagram. Whoa. Okay, so what I'm doing is I'm dividing our time into 2 times. Split up along there. Okay? So from when your feet leave the ground to your maximum height, there's no external forces on the system. The only forces are gravity, which is an internal force, which means it doesn't do work, and so the total energy is conserved. So you can figure out how much energy the system has at this point, and it's going to be the same amount as the energy had the system at this point in time. So this is 647 joules, and so you know the system has 647 joules at this moment. We can also calculate how much energy the system has at the very start. V is equal to 0 before he starts jumping, and so the kinetic energy, gravitational potential energy. Kinetic energy at the start is 0. The gravitational potential energy is 55 times 9.81 times 0.4. 216 joules. So when your acrobat went from not jumping to jumping with a full leg, the system's energy went from 216 to 647. So the amount of work done is 647 minus 216 431. Oh, that's the end of the screen, I'm sorry. So that's the amount of work. What did this work? It was the legs. The legs as it moved the center of mass up 0.5 meters. So 431 joules was work done by the legs. They're both in the same direction. So this is the delta y times 0.5 times the unknown force. Force is equal to 862 newtons. Is that the same as before? Yes, it's the same number. Oh, but you say, what about that's a 6 in that one. And it's not a 6 in this one. It's a 2 in this one. Yeah, the last digit is we're working with 3 sig figs, so the last digit is an estimate. So sometimes it's going to be different. It's going to be different because, you know, you did different algebraic operations, and so sometimes there's like truncation errors that come from you know, taking the square root and stuff. So the long story short is that we can use this concept of work to figure out how much force you get. But alternatively, one big issue here is that the way we define the system really does affect how we're calculating these things. All right, so that was 23. Now it's time for question 32. Come on now. Oh, there's nothing there. Hold on. There we go. 32. 32 reads like this. You push a blob of gelatin with a constant force of 3 newtons across a wet table on which it slides easily. Because the blob shape distorts, its center of mass moves only 3 millimeters during your time interval at which the point of application of your force moves 50 millimeters. What's the work done by you on the blob? How much does your force change the kinetic energy of the center of mass? Okay, so this is an issue we saw addressed in class when I was talking about this riddle of the spring. So here's the idea. You got a blob of gelatin, okay? And you go up to it, and you're going to push it. Give it a push, okay? The result is that the blob of gelatin changes shape and also moves. Okay, so in black here, I'll draw the center of mass. And what it's told us is that the distance between these, the change in the center of mass, is 0.03 meters. On the other hand, the point where you applied the force, this point here, this point has really moved quite a bit. And that's moved 0.05 meters. And so, how do you do these calculations? Okay, so the first element to this calculation is we're going to do some work. You know that it's the force pushes this way at 30 newtons. No, 3 newtons. Okay, so the moral of the story is that some of your pushing force went into generating system kinetic energy. That's because this thing is moving. The system has kinetic energy, and some of the work you're doing goes into changing the shape from a block to a squished block. Okay? So there's 2 different types of energy in the system. Some of it's internal, some of it's not. What work am I by the blob? Which one do I use? Which of these 2 numbers do I use? I'm going to use this number here, because the thing that determines how much work I've done is the change in position of the point of application of the force. Okay? F times 0.05. So that's 3 times 0.05. 0.15 joules. I've given the system that much energy. Okay. That said, some of this energy has gone into moving the system, changing the system's kinetic energy. Not all of it. Some of it went into, deforming the block. You think about it as like somebody throws a spring. The spring can hold energy inside of it in terms of compression or stretching, but the spring, if it has mass, it will also have some kinetic energy. So to calculate that, I just go force times 0.03. I think that'll work. Yeah, I think that's it. And the difference between these goes into deforming the shape of the gelatin. I think that's right. Question 45. Goes like this. Which arrangement in figure 9.45 requires more work to give the block a rightward displacement D? The springs, blocks, and surfaces are identical, and the springs are initially at relaxed length. All right. So which arrangement takes more work? So we're going to talk about this next class, I think. The deal here is that this rule that we've been using, F times delta X, essentially, it assumes constant force. That's essentially the reason why we used gravity to do all the examples in class, is because gravity on a particular object is always the same amount of force. With a spring, it's a different amount of force depending on where you are, right? So moving this one just a little bit to the right is going to require more force than moving it a little bit to the right over here. Because the closer the spring gets to the wall, the stiffer it's going to, the harder it's going to push back, right? What you do is you set up an antiderivative. F dx is the amount of work in terms of variables. So in both these cases, it's the same. Essentially because we're pushing the block in the same distance. The amount of force how do I explain this? So we talked about springs, and we talked about the amount of force pushed by a spring, and the idea was if this is the equilibrium position, the force is going to depend on how far away I am from the equilibrium position. Okay? So as I move the block from here over to here, I end up moving it over the same distance from equilibrium as when I move this block from here to here. the contact point to the spring, changes by the same amount. So since it's by a same spring, both of these are going to have the same force profile, right? So in this case, the spring pulls that way, and in this case, as we squish it, the spring pushes that way. But in both cases, it's the same force profile. We're pulling to the left. I guess you pull to the left, left is negative. Pull to the left, or in this case, we push to the left. Force, position, force, position. So even though the setups for these are very different, the displacement here is going to be the same, and the force, the response from the spring, the response from the system in terms of the force the spring is applying to the block are going to be the same. And that means that when you add up all of the work done by doing infinitesimal displacements, you get the same number. Whoa, that question's weird. Power is really fun. Power is units of joules per second. It's the rate work is done. And so, so the deal here is that we can talk not just about how much energy a force gives to a system, but at what rate energy is being given. And so in our modern world, the rate that force is being, the weight that energy is being transferred into the system is pretty important. And so the units of these are in watts. Yeah. So let's work through some problems. Essentially, I'm just going to be, I'll try to break it down. Okay, suppose a jogger has to exert a force of 25 newtons against air resistance. So here's our jogger, and his legs are pushing him forward. But the wind is pushing him backwards. Okay. The jogger has to exert a force of 25 newtons against air resistance to maintain a velocity of 5.0 meters per second. At what rate is the jogger expending energy? So how do we answer this? How do we figure out how many joules per second they are using? There's a relationship between V and all these things. It's more fun than it sounds. So let's have them move a certain distance forward. How far should we go forward? Nobody in the live chat. So how far should we imagine him go forward? Let's have him go forward 10 meters. Why 10 meters? Because it doesn't really matter how far in these questions. Okay, so how much work does he do in those 10 meters? The 10 meters are in the same direction as the force, so it's going to be plus distance times the force. So he has exerted 250 joules to go forward 10 meters at this velocity. Okay? How much time did it take him to go 10 meters? It took him 2 seconds. So the power is the work divided by the time. It's the rate energy is given to a system. It's 250 divided by 2, so that's 125 watts. Does that make sense? It's pretty fun. There's a variety of really cool applications of this kind of stuff. So 59, for example, hiking trails on steep slopes often zigzag back and forth. I went hiking to a really old park in, it was in Quebec, in the Gaspé Peninsula. And it had mountains shaped like this. Mountain. And I swear, they had some really old hiking paths that went like this. Straight up the mountain. Or hell. It was a hiking trail. It was a 60-degree grade hiking trail. It was terrible. So, to compare that with a more modern hiking trail, which might have something we call switchbacks. Switchbacks are shaped like this. So here's the old trailhead, and here's the new trailhead. You walk on the switchback, and then you switch back, 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 and you end up at the same place. So here's the fun thing. The fun thing is that the total altitude difference between the two is the same. So the amount of work that you had to do against gravity, pushing against gravity, mg delta y, total work you had to do is going to be the same. Okay? Here's the thing. Which one is going to take you, let's, compared to this jogger, okay? Which one takes more time? Imagine your jogger is running up these hills at, I don't know, 2 meters per second. So this one goes this way to the top, and this one goes this way to the top. They expend the same power or work. Which one takes longer? Small delta t for that, because it's a short path. Long delta t for that, because it's a big path. And it's long. It's really long. You go back and forth and back and forth and back and forth, right? So, as a result, the power work divided by delta t is going to be large for this one. You have to work really, really hard. You have to, well, work really, really hard. It takes a lot of effort to maintain that power. You're going to be sweating and overheating, whereas this power, same number, mind you, delta t long. This number is a big number, so the amount of power expended is lower. And so, it takes less effort to go on this trail than this one, even though the total amount of energy you need is the same in both. Does that make sense? 59, 60, 8. Oh, I didn't even do an elevator one. Let's see, is there an elevator one? Okay, I'm gonna do 68, and then I guess I'll. Really? I did that? All right, and then I'll do an elevator one or something. Is it possible for force to be exerted on an object along the direction of the object's motion and still produce no change in the object's kinetic energy? If yes, give an example. If no, explain why not. The answer is yes. What's the trick here? The trick is more than one force. Hey, what do I mean? Consider this example, our old friend above, okay? There's two forces on this dude. Two forces. There's... Actually, let's erase some of these. It's kind of... Okay. There's two forces acting on them. There is the force from the legs pushing you forward, and the force from the wind pushing you backwards. Because they're balanced, there's no acceleration, right? So the velocity's constant. No acceleration, constant velocity. Another way to look at this, though, is that my legs are giving the system power at this rate. That's how fast my legs are giving me energy. But the wind is taking out this much energy at exactly the same time. So that, because I'm putting energy in, but the wind's taking energy out, my overall kinetic energy doesn't change, and the speed stays the same. So that's an example. There are elevator ones too. I was hoping to find an elevator question. Give me a second here. Oh, I found a good one. This one's a little bit advanced, but we should have fun doing it. I don't usually teach power. It's weird that the 78. Okay, let me add this to the list. Alright. 78 goes like this. A 2,000 kilogram cab of a freight elevator is rated to carry a maximum load of 1,200 kilograms. But a careless worker fills the cab with freight that has a combined inertia of 1,400 kilograms. The worker then raises the cab 3.1 meters at a steady 2 meters per second. You notice an unfamiliar whine and come over to investigate. As supervisor, you know the motor has a 10% tolerance in its rated power output, and you must decide whether there's going to be trouble. All right. This question's pretty sophisticated, but it's fun. So how does an elevator work? The deal here is that you have a thing on the top, motor, and it pulls the stuff upwards. Tension, mass, okay? So the motor has a maximum power, okay? And that means that it can only exert energy at a certain rate. If it does pass that, you're in trouble. Okay, so here's the question. Here's how the question goes. There is a maximum designed amount of weight that the motor can lift at a constant velocity, etc. If your mass exceeds the maximum weight, it's going to take even more power for the motor to lift the thing at the same rate. So the question here is, what's the maximum power, and does the given question exceed the maximum power? And before we go too far, you could be like, what power, huh? Does it take... okay, so before we go too far, there's something nice you can recognize here, which is that that these elevator questions usually involve constant velocity. Okay? What does constant velocity mean? It means that the forces all balance. And so you can use, essentially, the argument we used up here to decipher how to do these questions. Okay? So let's imagine that we have an elevator. So let's start by finding the max power. So for the elevator, it says the maximum stuff in the system is M max is 3200 kilogram. And the velocity here is 2.0 meters per second. Okay. So the question here is, how much power does the thing exert? Okay. It also gives us the clue that the height is changed by, what does it say? 3.1 meters. Okay. So let's start this. What are the forces acting on it? Well, there's the tension force pulling the box up, and then there's gravity pulling it down. And gravity on this is 3200 times 9.81, 31400 newtons. That means that if you're moving at constant velocity, the net force is 0, and so the tension force has to be the same amount in the opposite direction. Okay? All right. So, how much work did the elevator rope do as it went from one point to another? The force from the rope is in the same direction as the displacement, so it's positive. 3.1 times 31400. So this is 97340 joules. So here's the thing. That's a lot of energy, but, I mean, a person could lift this elevator with a hand crank. They just do it really, 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 really slowly. If you want to be fast, the issue here is how much time do you have to transfer that much energy? If you're traveling at velocity 2 meters per second and you travel a distance 3.1 meters, then the amount of time it took is 3.1 divided by 2, 1.55, and that should be a t, not an x, seconds. And so the power of the elevator is 97340 divided by 1.55, 62800 watts. This is the maximum power. Except that it has a 10% tolerance, right? How do you interpret that? 10% tolerance says that this is only a conservative maximum power. The too much max power is going to be 1 times P. 10% more. 62800 times 1.1. So this is too much. 69080 watts. Okay, so the argument here is that you shouldn't use more than that power. You shouldn't set your elevator to use that much power. But if you do, definitely don't make it use more than this, because if you do, it'll break. Okay, so how much power did we ask it to use? Careless worker. The mass that they used was 3400 kilograms, which corresponds to F grav 3400 times 9.81 minus 3335. What am I using? 3 sig figs? Yeah. 33400 newtons. So the tension force to keep it at constant velocity is that many newtons. And so the work done is 3.1 times 4. No. 3400. 33400 times 3.1 is 103,500 joules. How much time did he take to give it? Same amount of time, because the velocity is the same. So the power is this energy divided by 1.55, and you get 66800. Okay, so the good news is that this one is less than the it's gonna break amount, but it's still bad. So go get mad at that employee. All right, that's it for this one, I guess. So what's that left to do? I think soon we're doing rotation, right? Friday we'll do some more. Okay, I'll talk to Jake and stuff about that. That's it for this week's online office hours. Have a good week. See you later.